Assalamualaikum and hi everyone. I'm the first presenter from Group 1. Today we will be present our SMPcache Simulator Project 1 for Set A, which include CEXP, EAR and COMP. This project helps us understand how cache behave when multiple processes access memory at the same time. Now let us introduce our team members. First we have Nurin, then I am NAJLAA, HAZIQ and IZUDDIN. I will be presenting about our introduction. In our introduction, we will be explaining the memory performance gap, where main memory is much slower than the CPU. Cache is used to reduce the delay by storing frequently used data. We analyze this using the SMPcache simulator with the CEXP workload to observe hit and miss rate. We also apply the principle of locating, where programs access the same or nearby memory location repeatedly, which improve cache performance. Move to our experiment task. The SMPcache simulator was utilized to obtain the specific miss rate for the CEXP, COMP and EAR memory traces with each simulation standardized to exactly 2000 memory accesses to ensure a controlled and fair comparison between programs. Next, we'll be moving toward the development. The simulation was conducted by configuring a cache-based memory system with predefined architectural characteristics. The parameters shown in the table 2.1 were maintained as constants to ensure a consistent and fair evaluation of cache behavior across all selected program traces. For the second simulation task, each program trace was analyzed to determine if they share the same locality grade, a process that identified if trace possess the best and worst locality, while evaluating how memory system design to exploit this pattern can significantly increase overall system process. For the third one, throughout the simulation, the real-time graphical progression of the miss rate was monitored to provide a scientific explanation for the why miss rate generally decreases as execution progresses, specifically focusing on the transition from the cold start phase to the steady state phase. Next, we'll be moving toward the development. The simulation was conducted by configuring a cache-based memory system with predefined architectural characteristics. The parameters shown in the table 2.1 were maintained as constants to ensure a consistent and fair evaluation of cache behavior across all selected program traces.
Hi everyone, I am Nurin and I'll be presenting the results and discussion section of our project. To understand our findings, we first need to look at the pre-execution environment, essentially the before state of our simulation. Now, let's begin. Let's start with the CSP workload. You can see the setup in figures 3.1.1 and 3.1.2. For this task, the simulator is configured for 2000 memory accesses. We are using 128 cache blocks with fully associative mapping and an LRU replacement policy. At the initial stage, every cache line is in the invalid state, as shown in figure 3.1.1. The graphs for hits, misses, and hit rates are all blank. This represents a cold environment where no data has been fetched yet. This baseline is important because we expect to see initial compulsory misses as soon as execution begins. Next is the EAR workload, shown in figures 3.1.3 and 3.1.4. Here, we are processing 5,308 memory accesses. We have kept the architecture consistent with 128 blocks and LRU replacement. Just like before, the cache starts in cold start conditions. All values for hits, misses, and bus transaction are currently at 0. This confirms that simulation has not started yet, giving us a clean state to observe how the specific workload begins to populate the cache. Lastly, we have the COMP workload in figures 3.1.5 and 3.1.6. This configuration uses 2,524 memory accesses. The cache architecture remains the same to ensure our comparison is fair. As you can see in figure 3.1.5, the system is in cold start state with all lines invalid. This baseline allows us to clearly see how the COMP workload initially struggles with misses before the cache warms up and performance improves. This concludes the pre-execution setup. I will now give it to IZZUL to continue with the after result analysis.
Hi, Assalamualaikum. My name is MOHAMAD IZZUL. So I will continue with 3.2. It is after result. So at the left diagram, it shows that text representation for after result CSP cache evaluation. And for right diagram, show that graphic representation for after result CEXP. Cache evolution. For next slide, we will discuss about simulation results for the CEXP workload. First, performance metric. For exceptional hit rate, it achieved a high performance of 99.260%. Next, almost every access satisfied at level 1 cache. Only 148 missed out of 20,000 total memory access. For marginal miss rate, it recorded at very low, it is 0.740%. Second is architectural advantages. It using fully associative mapping allow any memory block to occupy any cache slot. Drastically minimize conflict miss compared to other mapping technique and for locality optimization. Eventually, exploited both temporal and spatial locality. Next is simulation behavior and trend. First, observe a slight initial spike is missed during cache initialization. System stabilize almost instantly after the cold start, and for the long-term performance, there is hit rate sustained at nearly 100% throughout the remainder of the simulation. For lastly, it is configuration success. Proof that 128 cache block pair with LRU, it is least recently used strategy, is highly effective for this workload and minimize the need to reference main memory after the initial loading phase. Next, we turn to EAR cache. Okay, so on the left diagram show that the text representation for after result EAR cache revolution, and for the right diagram, it shows that a graphic representation for after result EAR cache evolution. Next, they have 3 for simulation result for the EAR workload. First, performance statistic. It is high hit rate, successfully achieved 89.902%. Successful hits achieved 4772 hits record out of 5308 total access, 536 total miss accurate during the run, and for calculate miss rate, there is record at 10.098%. For the second, it is behavioral trends. The hit rate increased significantly during the early execution stage. Stabilization point for performance level of at approximately 19%. After the first 1327 memory access and miss drop dramatically from an initial peak and remain constantly low. And the lastly is architectural benefits. It is demonstrate the district advantage of the fully associative mapping technique. Prove the 128 block cache size is sufficient to keep most required data resident, and confirm that the LRU replacement strategy is well suited for the EAR workload access pattern. Lastly, we have COMP-cache. For the left diagram, show that the text representation for after result COMP-cache evolution. And for right diagram, it shows that the graphic representation for after result COMP-cache. Next, we have simulation result for the COMP workload. For the first, performance metrics. It is moderate hit rate, achieve a hit ratio of 82.092%. Hit or miss count have record 2072 hits and 4452 miss out of 2534 requests. Miss ratio is calculated at 17.908%, and memory fulfillment is most requests fulfilled via L1 cache. Top less efficiently than previous workload. Second, trend analysis. Performance take longer to level off compared to CEXP or EAR. The hit rate reached at maximum point only after a significant duration, and the miss rate fluctuates constantly before eventually reaching a stable state. For third, they have comparative finding. For higher miss potential, results suggest a higher incidence of compulsory of capacity miss, and workload complexity for COMP demonstrates a more challenging memory access pattern for the cache to predict. And for the last, it is architectural conclusion. Using full associativity remains effective for supporting data flow despite workload difficulty, and the 128 block cache and LRU replacement policies still maintain a functional and efficient environment.
Assalamualaikum warahmatullahi wabarakatuh. My name is IZUDDIN. So I will discuss about result discussion. To begin relation, we assess the cache performance of 3 specific memory traces with CSP, EAR, and COMP. This value based on the configuration we established early in section 2.1. If you look at table 3.0, you can see the summary of our finding. CSP demonstrates excellent performance with a miss rate of only 0.74%, earning very good locality grade. EAR set in the middle with 10.1% 10% miss rate. CIP, however, struggles numerically, showing a high miss rate of 70.91%, resulting in a poor locality grade. Now we move to analysis of locality. As we saw, different progress SLP different degree of memory locality. CSP succeeds because its TE data requests close together while CIP fail to do so, leading to that 70% of miss rate. Second, regarding the miss rate, it is important to note that miss rates are usually higher at the very beginning of execution. This is due to cold start miss. Essentially, the case start empty as the execution focus and the case run out. The miss rate generally decrease and stabilize. Finally, the problem identification. The high miss rate in CIP indicate a clear memory bottleneck. To fix this, we could look at the hardware implements such as increasing the cache block size to improve spatial locality or simply expanding the cache capacity. Finally, to conclude our analysis, lead us to 4 main takeaways. Firstly, cache efficiency is not just about hardware, it depends heavily on the memory access pattern of the software itself. Second, we have to remember that hardware cannot fully fix any efficient software if code has poor locality, a better case only do so much. Third, patching is a key. Performance almost always improve after initial code start phase. Ultimately, the best system performance comes when successfully match the software behavior with the appropriate case design. So that's all from us. Thank you.
Nice.